that Shafaq has, our Lagrange density was this, right? So this is phi star phi really, right? Mod phi squared is phi star phi. Okay, now we want to make a variation. So this is the Lagrange density we should write down. You know, when you derive the action, when you write down the equation of motion, it's always good to start with the action. So the action is integral of this quantity d4x. Okay. So now we vary the action with respect to phi and set it equal to 0. That is our variational principle. And so we have from here 0 equal to integral, right, d4x. I always write the d4x first. So we have two terms. One is del A delta phi, del A phi star. So we are now making a variation with respect to phi star, but we can also make a variation, with respect to phi, but we can also make a variation with respect to phi star. We'll do that later. So that's one term. And then we are not varying with respect to phi star now. And here, what we will have is, I'm just doing it one step. So mod phi squared. So v prime is a function of this one variable mod phi squared, but then we make the variation of mod phi squared with respect to phi, and what remains is phi star. Okay, is that clear? And now this one, we do the standard integration by parts, drop the surface term, and when we do that, what we get is, so there's a delta phi here, sorry. Phi star delta phi, because when you take the variation of mod phi squared, which is phi star phi, you get phi star delta phi. Okay, so this is equal to integral d4. I'm writing in one step. So what we get is when we flip the derivative onto this, Shafaq, are you with me up till now? Shafaq?
Yes, sir.
Yeah. So
I'm
you
here,
get
sir.
minus mod squared phi star.
That's what I was saying, sir.
Yeah, you're absolutely right.
Yeah.
I wrote a box squared phi, but you know, when I take the variation with respect to phi star, I'll get the box squared phi, right?
Yes.
So that's what I meant. Okay. So v prime mod phi squared phi star delta phi. So if this is 0, then the equation of motion, you're absolutely right. When you take the variation with respect to phi, you get the equation of motion for phi star and the other way around. Okay. So that's the equation of motion for phi star. So this is equal to 0 and this is equal to, by doing the variation with respect to phi star, what you will get is, this is something you can check, but it's obvious that you'll get this. Yeah, there's a question for somebody?
Yes, sir. Yes, sir. So in this whole moment of internal symmetry, this symmetry does not...
Wait. Is this clear up till now?
Yes, sir. Thank you.
Okay, so Shafaq, is your question answered? Yeah, so
yes,
now
sir.
let us go to the next question, which is from
Akshay, sir.
Akshay. Okay, Akshay. Can you answer?
Sir, in the whole argument of this internal symmetry, this does not look physical. Time translation symmetry, space-time translation symmetry, that looks physical. Over here, I have an hypothetical scalar field which in phi 1 direction and phi star direction, and I can take a certain angle at the...
No, wait, you're mixing things up. Last time, we actually did two things. First, we had two scalar fields with the same mass, right? Two real scalar fields. And then what we found is an O2 symmetry.
Yeah.
SO2 symmetry, right? Okay, was that clear to you?
Yes, sir. Yes, sir.
So what is your question?
So the point is, this type of... how it is exactly related to my system. Changing phi by some phase how this exactly related to my system.
Your system is described by the action we wrote down.
Yeah.
That action has this property. Okay. Now the question is, with this property, can we actually predict any part of nature? The answer is yes. What we're trying to predict, you see, is electric charge and other charges as well, like I mentioned in answer to Ruksha's question. But at least electric charge is certainly covered. And that, you see, I was trying to show by going into the complex basis of fields by defining phi and phi star. What I showed from there, so the most important point was that U1 symmetry. So the U1 symmetry was like delta omega phi is equal to I phi, and delta omega phi star is equal to minus I phi star. And these transformations actually left the Lagrangian invariant. Okay. And therefore the action is also invariant. That is the statement of the symmetry.
So point is, sir, this.
So now, no, wait, hang on. Now, from here, what we found is that there's a conserved Noether current, right? Conserved Noether current. JA, which was given, if I remember correctly, by I, phi, del A, phi star, something like that, right?
Complex conjugate, minus of
phi star, yeah. So that was a real current. It was a real 4-vector current. And from here we constructed Q in the usual way, right? Integral dqx J0. And then what we saw was that this Q actually generated, so what we found is that phi with Q actually generated delta omega phi. And similarly, phi star with Q did the same. Phi star. And because this was I phi and this was minus I phi star, so this is in the Poisson bracket sense, you see.
Yeah.
But then we sort of drew an analogy, you see, with quantum mechanics. In quantum mechanics, what you know is that if you take the commutator of any quantity, let's take a commutator of something like a vector field, V, right? V, some component, let's say alpha, with L, beta, in quantum mechanics, right? We know what this is, okay? We know what this is. This is epsilon I, epsilon alpha, beta, gamma, V gamma.
Yeah.
Right? This you know, so in terms of operators, right? So what this means is that this is the transformation property of a vector in quantum mechanics. So when you get something like this, so you can say that this vector operator has charge +1, if you wish. Likewise here, in the Poisson bracket sense, we said that phi would have charge 1 and minus phi star, sorry, I've got a star here, would have a charge -1. So this is basically what we said might be happening. So this was kind of a guess, a physical guess, that this U1 symmetry, the generator of the U1 symmetry is Q, is one generator, and this generates the right kind of transmission, which tells us that we can then think of we can then think of the field phi carrying a charge 1 and field so the field phi. So another way of doing this is actually going to a basis in which you look at the diagonal, look at the eigenvalues of Q, and then the eigenvalue of Q corresponding to phi in the operator sense would be +1, and the eigenvalue of Q. I mean, this is how you derive spin, right? This is how you talked about spin plus, spin half and spin plus half and minus half eigenvalues in angular momentum, right? So I'm assuming that you're familiar with that. So that is what we use to say that phi has charge 1 and phi star has charge -1. However, this is up to what we came to last time. But there is this other question which I was telling Ruksha, namely that, you know, if you have a system sitting there with electric charge or whatever charge, who cares, right? I mean, unless that system, that material system, interacts with electromagnetic fields, we don't really know, right? We don't really know if it is electric charge. Another way of saying the same thing is that our four-vector potential would be a probe of electric charge. So how it couples to this field phi and phi star would actually say whether these fields carry electric charge or not. Do you understand the physics? Is this okay? We now need to probe U1 charge by coupling JA to AA. This is an electromagnetic field, electromagnetic vector potential. Is this clear that we need to do this probe? Without doing this probe, for instance, suppose the phi is some other U1. So the U1 may not be electrodynamic U1, it could be some other U1, let's say a phi-on U1. So maybe the conserved current we found corresponds to phi-on conservation. If that is the case, then we don't know if this is going to couple to electrodynamics. In fact, the electromagnetic vector potential would then not see this charge at all. It will not couple to it. It will not talk to it. Okay, so that is the key question. Does our electromagnetic vector potential talk or meet or interact with this current? So what we will do is we'll try to make the field interact with the current and then see some consequences. However, I found that there is an easier way of doing this, and through this I'm going to discuss some new features of field theory, of classical field theory, which is usually not discussed in textbooks. Now, some of you may be a little angry with my approach because, well, not many of you are here today, so that is probably a good enough reason. I see only some 18 persons out of 33 have landed up, which means 15 haven't, and I don't know why, unless they are not well or something. Oh, by the way, I hope none of your classmates are suffering from the disease, right? Is there anyone whom you have heard is infected or something?
Sir, Shomo.
Oh, what has happened to Shomu? He has tested positive?
Yeah, yes, sir.
When was this?
That I exactly don't know, but his family and completely, they all got infected.
Where does he stay?
In Boram.
Barampur. Oh, that's a shame. That's not good news. So let us all recover. Let us all hope that Shomo will recover quickly. Okay? I hope you will join me in wishing Shomo a speedy recovery. He will recover, I'm sure. And his family members too will recover. Oh, that's, I'm sorry to hear that. Okay. Anyway, so, but Shomo came to last class, so it must have been between the last class, between Thursday and today, right?
It's been over a week for him. He's been having symptoms since last Monday.
Oh, I see.
Yeah, he's kind of on the way to recovery, but his entire family also got infected.
I see. So he's on the way to recovery. Okay, good. So we'll expect him back soon. Okay. Thanks, Shifa. Right. So we need to do this probing, and we need to see how we can couple the electromagnetic field. And in doing that, we will discover some fantastic features, some completely, totally unexpected features. Okay. And I like to do this because, well, it's not textbook material, it's not there in Landau. So this is going to be some fun. And, you know, so if there are questions, of course, we'll address those questions. This is also probably, you can say, out of syllabus. So anyway, how are you going to do this? But before that, I thought I should introduce to you a new method of writing Lagrangians, and it's called the first order formalism. Now, in the first order formalism, that's a bit like saying treat the momentum P as independent of velocity. Okay, now you will remember that we did such a thing for particles. We did such a thing for particles, and we were able to write down an action from which the standard Landau-Lifshitz action could be derived by varying that action with respect to P and using the solution and putting it back into the action, right? So eliminating P using its equation of motion, we were able to get the standard Landau-Lifshitz type of action for a free particle, which is only a function of the forward velocity. I think you remember that, right? Is there anyone who doesn't remember or who's totally forgotten this? Because that particular way of doing it had some advantages, that it enabled us to write down the action for a particle with zero mass. Okay. And I think there was some discussion of this in your tutorial with Oritso also. I'm 100% sure about that, but it may be. Okay, so this is something that we're going to extend that idea to field theory, to classical field theory. Now, why do we want to do this? The reason we want to do this is because you'll see that the coupling of the conserved, so again, we'll have the same action that we derived with, but with some new variables, okay? And of course, the first thing we will do is to prove that it is the same action, so that you are convinced that I'm not doing something hanky-panky. So, so the point is that we introduce a new action. Okay, so let's go to the next page, which is equivalent to this action. So this is kind of fun. So we begin with this action. Okay, so this action involves some new vector field G, GA, and its complex conjugate. So this is a complex vector field, 4-vector field. And of course, it's also functional of phi and phi star. And what does it look like? Well, it looks very simple actually. P4x, GA, del A phi, plus G bar A, which is the complex conjugate of GA, del A phi star, minus GA, G bar A, minus V of mod phi square. That's the same as before. Now the question is this action the same as the action we wrote down last time? Yeah?
This is just one notational problem. Why we are not using G star over, why we are using G bar?
Because it's easier for me to write down bar than star. That's why on this board.
But actually, we are doing the same thing for this phi. So therefore,
yeah, well, you can write it phi bar. I don't care.
Okay.
Right. Okay. I just didn't write phi bar because that was the first time you were introducing it. But okay. I mean, you can write phi bar. So if you want, I can change to phi bar. For me, it's easier to write phi bar. So, okay, so following Akshar's suggestion, we can move to phi bar. Just to remember that bar is nothing but complex conjugation. So that will make things consistent. But first we have to see whether this action is actually the same as the action we wrote in the last page. Excuse me. Yeah, so to do that, what we do is we make a variation of this action with respect to g, let us say. And we set it equal to 0. And when we do that, so what do we get? Well, when you do a variation with respect to g, we get a delta g a, del a phi, and nothing else. So phi is not bothered because g and phi are completely independent variables. G and phi have nothing to do with each other at this point. So when we set it equal to 0, when we make a variation with respect to g, we don't worry about phi. And nothing we worry about here because g bar a is also independent variable. But we do get a term from here, which is delta g a, g bar a. That's it. So that is equal to 0 for arbitrary variations delta g a, and from here we get a g bar a equal to del a phi. Is this clear? I mean, it's very, very simple, right? And similarly, if you do the variation with respect to g bar, you'll get g a equal to del a phi bar. I'm not doing the calculation, but I think it will go exactly the same way because you can see the g bar, the bar and unbar symmetry is obvious from here, from this action. So now we get this as a solution for g and g bar in terms of the derivative of phi and phi bar. So what we can do is plug it back. And we get an action which I shall call S prime. And this action can only be a function of phi and phi bar because we are plugging in for g and g bar. And let's see what that is. So we get del a phi bar, del a phi plus del a phi bar minus del a phi bar, del a phi minus v. Okay, and now we can see that, lo and behold, it's exactly as previous. Okay, so what we have shown is that this action, okay, is equivalent to the previous action for a complex scalar field if we take the variation and use the equation of motion to eliminate g and g bar. Then we get back the previous action. So you might ask, why worry about this g action? Why not just stick with the previous action? Well, there are certain advantages. So first of all, we do is, we already know the equation of motion for g. We've already solved this, but we go back to this action, and ask, what are the other equations of motion? Okay, which means that now we want to consider del phi s, the previous s, and set it equal to 0. Okay, and let's see what we get from there. We get, well, this one is del a delta phi, and nothing here. So we are going back to this action and making a variation with respect to phi. Okay, so nothing comes from here, nothing comes from here. From here, we get v prime mod phi squared, phi star. Sorry, I missed something here. This is not a del A. Yeah, I missed it. This is not a del A. So this is a GA. Okay. So is this clear now that that's what we have? And from here, then we get the equation of motion. So we do the same thing. We flip the derivative onto GA, and we drop the surface term, and this one stays as it is. So from here we get the equation of motion del AGA plus V prime mod phi square. Sorry, I said phi star. We should go back to our current notation, which is phi bar. This is phi bar here. And if you do a variation with respect to phi bar, you'll get the same kind of equation, looking very similar. So these are the equations of motion obtained by variation with respect to phi and phi bar. Okay. So now we have all the equations. When we do variation with respect to G and G bar, G and G bar give us these equations. And when we do a variation with respect to phi and phi bar, we get these equations. Okay. So we have a complete set of equations. Good.
So should there be a phi bar in the V next to the V prime term?
Sorry, where?
Instead of the phi bar, just if you just missed it.
This one?
Yeah, shouldn't it be phi bar?
No, you see, because we are making a variation with respect to
Oh no, yes,
phi bar here. That is why we get the phi. Okay. So variation is with respect to phi bar. But what is left, you see the whole thing comes from here. Mod phi square is phi bar. So when you make a variation of that with respect to phi bar, you're left with a phi. All right? Shafaq, is that okay?
Yes, sir. Thank you.
Yeah. Okay. So now we're going to look at something else. We're going to look at a set of transmissions, okay, which leave this invariant, and that's also going to be a U1 symmetry. And we know what that is. We know that this is delta omega phi equal to I phi. We know this already. And what we now need is G. And G actually goes to the other thing. How do I know this? Well, you can see that if I make these transmissions, then this will leave invariant. So the action doesn't change. And therefore it's a U1 symmetry. Okay. So we found the U1 symmetry by looking at the action and noticing that these are the transmission properties. Now, having done that, we now can, of course, it is clear that the Lagrange density also doesn't change under the omega transmission, U1 transmission. But then we can do variation directly. So let us do the variation directly of this action. So we are now dealing with the first action. First action. The Lagrange density corresponding to this action, whatever is inside, right? So we are going to use that, but we're going to do things carefully. So what we will get is delta GA. So so delta omega GA del A phi. I'll write the whole thing explicitly so that you don't have any difficulties. So that's the first term. The other term we can write down directly. So delta omega G bar A del A phi plus G bar A phi bar, sorry, delta G bar A del A into omega phi bar, okay, minus delta GA G bar A minus minus let's write it, delta G bar A GA Okay, and yeah, so okay, so now what we see is that we are only interested in the derivative terms because that alone will lead us to the conserved current. The rest will be equation of motion. So I will not do this exercise, but using the equation of motion, equations of motion, this can be written as del A phi delta omega GA plus phi bar delta omega G bar A. Okay, so this is equal to 0 just from this equation. And this one, you see, delta omega, now we can put the, so we are using the equations of motion and the variations. So it is an exercise I haven't done. I'm leaving it to you as an exercise. So this is an exercise that this will come out to be like this. And now when you plug it back, we get that we have a conserved current. Oh, you're out of space. So let me just make some room here and say that we get del A JA equal to 0, where JA is I, GA phi. Did I get it wrong? Should be minus, right? Phi. Yeah, this should be a minus sign. Phi minus G bar A phi bar. Some mistake here. Hang on. No, this is an overall sign problem which I don't understand. Which overall sign is off by a sign. I think there is a mistake here because I'm sorry. I'm sorry. I'm sorry. Yes. No, this is yeah. So yeah, I made a mistake. Hang on. So let me go back. I made a mistake because I skipped a step. This is the problem is always skipping a step. Okay. Right. Yeah. So this is 0. This much is clear. So let me erase everything. Well, is this part also? So remember that when we derive the Noether current, it's the delay delta omega phi and delay delta omega phi bar from where we get the conservation law. Rest of it will be just equation of motion. So you plug in everything and show the equation of motion. So what we get from here is this. We will get, so if you take this, this comes out, and what we get from here, yeah, so it's from these terms that the conserved current will come. And the rest will be equation of motion. Okay, I'm not showing that, but I'm leaving it for you to see that if you use these terms, the derivative will come out, and what we will have is GA, that was my mistake, delta omega phi, that is the way I wanted it, right? Plus G bar A, delta omega phi bar. Okay, so JA is now GA delta omega phi. I'm not plugging in the delta omegas yet for reasons that will become clear to you in a second. Okay, so JA is this. This is our JA now. Once again, you can see that it's exactly the same JA that we found from the previous action. If you plug in, using the equation of motion, if you plug in what GA and G bar A are, then you get exactly the same current. But here I wanted to have you have a look at this. Why? Okay, good. See, this form, yeah, that was the. So is this clear? Are people confused with my mistake? You shouldn't be, right? So is this clear that the conserved current will come from these terms? So this del omega equal L equal to 0 is this. The conserved current will come from these terms. All the other terms will vanish when we use the equations of motion. Okay, so I haven't shown that, but I think you can show that easily. It's very, very simple. We have the equations of motion, you just plug it. Okay, so if there's a question, you should stop me, right? Now, right, so here, let us look at now, go to the next page and look at the Noether charge. So what is the Noether charge? The Noether charge, U1 charge, is d cube x. Okay, we have G0, right? G0 delta omega phi plus G bar 0. That's the way it looks, right? And what we know from our equation of motion is that G0 is del 0 phi, right? Which is the same as pi. And G bar 0 is del 0 phi bar, which is the same as pi bar. Pi and pi bar, well, earlier I was calling this phi bar as phi star and pi bar as pi star. But if this is the case, then you can see immediately from here that phi with q, Poisson bracket, will automatically be delta omega phi because of these relationships, right? And phi bar with q, Poisson bracket, will be delta omega phi bar. So it's automatic, right? So then, the generator expressed in this form and using the equations of motion, which we have to anyway, use the equations of motion. So G0 and G0 bar are simply given by these relations. They're related to pi. The other G's, you see, do not relate to any canonical conjugate momentum. The other G's do not relate to any canonical conjugate momentum. So this is adequate. It is adequate that we have just these guys. Okay. And you can also verify that acting on GA and GA bars, we can also verify that this is true. GA on Q, Poisson bracket, is indeed delta omega GA, and so on. As you would expect. So acting on all the fields, the Noether charge Q generates the correct U1 transformation. Okay? Good. Now we shall do something extraordinary. Now, so we have a current. So let's write down so let's go back to the current. The current is JA, the Noether current. The U1 Noether current is JA, given by GA. Now I shall write down what the delta omega phi's are, so I get this kind of relation.
Sir.
Yeah.
Yeah, initially it was defined for the previous section that phi is equal to del 0 phi star. This time it is del 0 phi. So is it, will this one work also? That's why it's written like that.
No, you're right. It should be phi star.
Because I thought that even GA was defined as del A phi star.
Yeah. So what I mean is this is pi. So I don't need this expression at all. What I mean is G0 is like pi, and G0 bar is pi bar. That's what I meant, okay? So it's the
Sir,
same. The equation of motion, G0, okay, let's go back.
Sir, I guess you mismatched the
So the
problem.
equation of motion is, yeah, I made a mistake. Actually, G0 is pi, because del 0 phi bar is pi, right? Remember? Yeah, who asked this question? I mean, I'm sorry, I couldn't see who
Sir,
asked it.
it's Aditya.
Aditya, yeah. But you see, Aditya, so what was pi? Pi was del 0 phi bar, right?
Yes, sir.
So GA is pi, right? That's what I meant. That's what I meant here.
Okay.
So G0, sorry, not GA, G0. G0 is pi. So forget about this, should be a phi bar, you're right.
Okay.
Yeah, this should be a phi bar and this should be no bar. Okay. Right. So everything is okay because pi comes here, and when you do this, it's pi with phi, which is the delta function. That is how you get this. Is that clear? Yeah.
Yes, sir.
Okay. Yeah. So now let's get back here to the current, and now couple to A. Usual noise coupling. We discussed this earlier. Sorry, I forgot to expand. Yeah. So usual noise coupling. So what we are saying is we are going to introduce an interaction term. Just like we did for particles. Right? And what this is, we can write down immediately. I integral d4x Ga phi minus G bar A phi bar AA. Okay, so that's the kind of interaction we're going to introduce. All right? And when we do that, we have the full action now. The full action, so this leads to S full, which will involve, what is S full? S full will be so, well, I should perhaps write it down as fully as possible. We have Ga del A phi plus G bar A del A phi bar minus Ga G bar A minus V of mod phi squared plus I Ga phi minus G bar A phi bar AA, and another term, which is your favorite term, which is something we all know, namely minus 1 over 16 pi C FAB. Maxwell term. So this is the complete action where we know what FAB is. FAB is del AAB minus del BAA. So what we have done now is we have taken our scalar field action, coupled the current, the conserved U1 current, to the 4-vector potential, and also included the electrodynamic Maxwell term, FAB. Okay, so this is the full action. And one of the home tasks is to write down the equations of motion for this action. Okay, so that's one of the things that I shall like you to do. I shall do a part of it, namely I shall do the variations with respect to G and G bar and with respect to phi and phi bar, and leave the rest to you. I shall not make a variation with respect to A, because that part we know. That will be the Maxwell equation del A FAB equal to JB 4 by pi C. So there should be some 4 pi by C, but never mind the 4 pi by C. I always ignore that. Yeah, there should be some C factors and so on, but I'm ignoring them completely. So it will be your job to put all the C factors, the velocity of light factors back and get the thing in order. But that will just be a term here, some constant here with C and so on, which you'll have to worry about. Okay, so what I wanted to show you is what this does to the equation of motion, because we can see immediately that right away that there will be changes. So if you make a variation with respect to G, right? So delta G S full equal to 0. What does this give us? Well, this gives us delta G A. So there's an integral d4x. Delta G A del A phi. Nothing from here. Here I get delta G A, G bar A. But I do get some terms from here. I get nothing from here, but I do get some terms from here. I get, in fact, plus I delta G A phi AA. That's the equation of motion. So what does that give us? That gives us, so G bar A, it gives an equation for G bar A. The delta G A goes out as a common factor. So G bar A, what is that equal to? It is equal to del A phi plus I phi. Indices problem, always a problem. So raise this, lower this, so that every term has up and down contraction. So this is phi AA. Okay, so we found a new equation of motion, because earlier it was G bar A was just equal to del A phi, but because I've done this coupling, noeta coupling, I get I phi AA. Okay, and also then I don't have to do this, but you can, read it off or do it if you want. And this will be, earlier it was del A phi bar, but now I shall get a minus I phi bar AA. Okay, so you see that there are differences now. There are differences coming up from these terms. Okay, and now you can also do the variations with respect to phi and phi bar. So let us try to do that. Those are non-trivial variations. So I would like to, unfortunately this page is over, so maybe I should do the variation right here, write down the answer for you. These are not difficult calculations, right? So when I do a variation with respect to phi, what I shall get is, I'm simply writing down the answer, minus del AGA. I'll get that from this term, nothing from here, nothing from here. I'm doing a phi variation, mind you. From here, I'll get minus P prime phi bar, right? And from here, if I do a phi variation, I'll get plus I G A AA. So that is equal to 0. And the other guy, I should get just a complex conjugate from here. So let's calculate the complex conjugate. So we can change the signs here just for the plus sign, this to a minus sign. To 0, and the other term should be del A G bar A. No mistake. Del A, or so I missed a plus here. Del A G bar A plus V prime phi. Now here it will be a change because there's an I there, so I should get a plus I G bar A AA to 0. So now we have the complete set of equations of motion. This is one, this is the other, and these two correspond to phi bar and phi bar variations. Okay.
Sir, can you repeat the last two lines? Actually, your video was pausing.
Video was?
Pausing, sir. Sir,
Oh,
after defining, after getting GA and GA bar, what we actually did, sir, means
no. So GA and GA bar equation of motion has been derived.
Okay, fine.
Now I am doing a variation with respect to phi and phi bar. So the
Okay,
variation
fine.
with respect to
Okay.
phi will lead you to this equation. Variation with respect to phi bar will lead you to this equation.
Okay. Got it.
Okay. Yeah, right. So let's see, what do I want to do? Yeah. Yeah, actually, what I want to do, you see, these we can leave for later on. What I want to do is I want to substitute these equations back into the full action. Okay, so substitute the G and G bar into the full action. That's what I would want to do. Okay, is that okay? Is that clear? What I'm trying to do? I've obtained G and G bar expressions from using the variation with respect to the of the full action with respect to them. And having obtained this, I want to plug them back into the G action. Okay. So when I do that, so let's go to the next page. This is a little tricky because I can't see the previous page. So what I do is plug back solutions for GA and G bar A into S full. So this gives us a new action because I'm plugging back for GA and G bar A. And so S, let's call it capital F. And now we are back to only our phi and phi bar variables and of course A because of the Maxwell part. And what do we get here? So I'm okay, if you pardon me, then I should only write down the well, I should work it out. Oh, sorry. I should work it out. So I have to see this. GA is this and G bar A. So this is G bar A and this is GA, right? So let's substitute that. It's a little bit of algebra, okay? And I sometimes feel lazy to do the algebra, but you shouldn't feel lazy to do the algebra, right? So we have GA del A phi. So GA was del A phi bar. And what else was it? See, I forget. And then what else was it? So GA was del A phi bar minus I phi bar A. Okay. Minus I phi bar AA times del A phi, right? Correct. And what we get for the other guy is del A phi plus I phi AA times del A phi bar. Okay, and then we get minus, we get GA G bar A. So GA is del A phi bar minus I phi bar AA, and G bar A is del A phi plus I phi AA. That's it. And the other terms we have are known because that's just V, and then minus 1 over 16 pi C FAB FAB. Okay, so now I'm going to be lazy and write down the answer. The answer is kind of weird. It's del A phi, dA phi. I shall tell you what that means. Okay, minus V of phi mod phi squared minus 1 over 16 pi c. Now I'm not doing this exercise, so because if I do everything, what will you do, right? So you have to verify this. So there's an exercise here where dA phi equal to del A phi minus I phi AA, and dA phi bar. So that's the definition of dA phi, and dA phi bar is del A phi bar plus I phi bar AA. Okay. So I actually this is not a difficult task. You just have to look at all the terms and you see that this is true. Okay. So what you do is you plug in dA and dA phi and dA phi bar from here, and you write it up and see that these two check. Okay, and they will check. If they don't check, you can tell me that they don't check, and we'll see where we went wrong. But they will check, I can guarantee you. So if we eliminate GA and G bar A by using their solutions of their equations of motion into the full action, we get a new action which is only a function of phi and phi bar and A. Okay, and this is the final outcome. Okay, and here is the entire magic. Why do we want to call this the U1 of electromagnetism is right now going to be clear to us. Provided, of course, we are identifying the AA as the electromagnetic vector potential. Okay, so let me show you some new things. First of all, remember the previous action, the previous scalar field action, del A phi bar minus V of phi, etc., had a U1 symmetry, right? And U1 symmetry, so I'm going to now talk about U1 symmetry slightly differently, but we did this earlier. So the U1 symmetry meant that U1, so this was the earlier U1, this went into phi tilde, which was e to the I omega phi. And phi bar under the U1 symmetry went into a phi bar tilde, which was, because it's complex conjugate, it was just this. Remember that? Remember this we did last time, in the last class on Thursday. Okay. And where omega is a constant. Space-time independent constant. Okay. Now, what we're going to do, let us make omega a function of space-time. Okay. So when we do that, what we find is that del A phi goes to del A phi tilde, which is, see earlier, del A, when omega was a space-time independent constant, the partial of phi, del A phi and del A phi tilde and del A phi bar tilde were transforming in an identical way. Because e to the I omega into e to the minus I omega would simply come out of the derivative. But now we can see that if we make omega a function of space-time, then del A phi tilde will be del A phi, will no longer just be equal to del A phi, but there will be an extra term. And what is that extra term? I del A omega phi. Correct? And similarly, del A phi tilde, phi bar tilde, bar is equal to del A phi bar minus I del A omega Fine. So now we can realize immediately that the previous action, del a phi bar minus d of phi, that will no longer have an invariance when omega is a function of omega of x because of this extra term. Because of this extra term. Okay, this delay omega term. The delay omega term would mean that if you now calculate delay phi tilde, delay phi bar tilde, you will get the previous term, but you'll also get a term which involves omega. And omega, this function we have chosen, is our choice. So we have this unsavory feature that in this case, our previous action is no longer invariant. But let us look at dA phi. So what is what is dA phi? So we have now given our interaction the way we propose the interaction. This here is the entire action. This is the full action, this last line here. So we can ask, what is dA phi? Okay. What is dA phi tilde? Well, dA phi tilde from here, from the definition, would be del A phi tilde minus I phi tilde and AA tilde. Because now omega is a function of x, so maybe we should allow for A to change as well. See, earlier when omega was a constant, we did not think of changing A. But now that we are making omega as a function of x, maybe we should allow for that change. And let us look at what this is. So you can see immediately, I can skip a step also, that if del A phi tilde is, so from here, del A phi tilde is this. So this is, I can write this as dA phi. No, sorry. So let me just write it down. Del A phi. Okay. Okay, there's an, I think it's best to write down into the I omega as a common factor because that's always there. So phi tilde, remember, is into the I phi. So into the I omega always go here for a ride. So this is del A phi. And we get I del A omega phi. And from here, we get minus I phi tilde. So, sorry, phi tilde is into the I phi, so we don't have to write phi tilde. And we write A tilde. Okay, and e to the I omega is outside. Okay, this is what we have. But you can see if A tilde A is equal to AA plus del A omega. Namely, if A tilde is related to A by the standard electromagnetic gauge transformation, which we have discussed endlessly before, so that's just a gauge transformation, EM gauge transformation, which of course leaves the Maxwell term invariant. So that's a EM gauge transformation. So if you make that kind of a gauge transformation, then you see this I del A omega, the omega dependence drops out, and what we are left with is e to the I omega dA phi. Okay, so we have this fantastic result, which we did not anticipate before. So now you can see that if you have dA phi tilde is e to the I omega dA phi, then this action no longer has an omega dependence because dA, so also from here you can say that dA phi bar tilde will not be nothing but, this is again an exercise, but you can see that this will be easy to prove. Okay, using this definition of dA phi bar. So it's a bar over everything, not just phi, but it's a dA phi bar because it's a complex object. Okay, so Yeah, sometimes my bar and tilde look similar, so you should point out if there is a problem anywhere. Here I should write the tilde like this. There's always a tilde, there's a bar tilde. So all these things. So once we have this, you see, dA phi bar, when I make a gauge transformation, when I make an omega transformation which depends on x, because of their transformation property, the omega dependence cancels out from here and we are left with an invariant action. And of course, everything else is independent of omega. V phi squared is independent of omega, FAB by definition is gauge invariant. So what we have found is that our Noether coupling led to electromagnetic gauge invariance. And this is the final seal because we know that electromagnetism, the theory of electromagnetism, Maxwell's theory, has this wonderful property of gauge invariance, and we were able to derive it by doing a Noether coupling. We didn't do anything fancy. We took our Noether current, okay, and simply coupled it to A. Now you can ask, why didn't we just do it in the previous action? Why did we have to go through the G and G bar, all that kind of shit? Well, it's because this made life very simple for us. You could have done that, but then you would need 2 steps to do that there. Okay. Now, here I would say that many of you might find this a little difficult, what we discussed today, because it's not discussed in textbooks. However, if you can convince an elder brother of yours, who's Shumon Ghosh, who is an elder brother in the sense that he's a year senior to you, he is doing a project with me on exactly this. So this particular part, he'll be able to explain to you very, very easily. And you can, if you can't get him, you can at least ask him for this part as a write-up. Okay. So if he doesn't want to give it to you, well, you have the write-up from me. One part of this is that you'll have to do all the derivations which I didn't do, which I skipped. If you go through all the derivations, then you will find that this beautiful property appears. The electromagnetic gauge invariance comes out of the Noether coupling, and this is the seal that yes, there is a U1 for electrodynamics. Okay, and electromagnetic gauge invariance is actually implied by the coupling of the conserved U1 current with the 4-vector potential. Okay.
So I have a question.
Yeah. Go ahead, ask your question.
So over here, the electromagnetism is coupling with the scalar with phi.
Right.
So the point is, in reality, what is the scalar field?
In reality, the scalar field is a model for anything which has charge. The scalar field is the simplest model. We could have taken other fields like a fermion field. The electron, for instance, would be a fermion. The electron has a different equation of motion, and I don't know if you have read the Dirac equation, so I didn't want to get into that. If you haven't read the Dirac equation, then I can't possibly use that in our class, can I? So I wanted to wait. But, what we did was something very, very simple. So let us have a sort of a summary. First we did...
Okay. So what are the scalar fields with which the electromagnet interacts? Does it interact with, let's say, temperature field, or let's say...
The electromagnetic field will interact with anything carrying a U1 charge, okay, which has this property of gauge interactions, gauge invariance. So we have proved now, we have not suggested that this is how we do it, but we have actually proved that all we did, you see, was start with a scalar field. A scalar field is the simplest example where this happens. This is the field which Higgs used originally. So this is actually also called the abelian Higgs model. Okay, Higgs used it. And I can actually go to the Higgs mechanism one step from here, but I will not do that. That may be a little too advanced. But the Higgs mechanism is just one step away from here. It's very, very easy. It's very easy to get there. But this is the model that Higgs constructed. And he constructed it just as a toy model. Any toy model of a charged scalar field interacting with electrodynamics. And what he showed was that you have this gauge invariant interaction. So obviously this action, the final action S capital F we wrote down, had this gauge invariance. Okay, we did not put the gauge invariance to begin with. We had a global U1 invariance. By global, I mean the transformations involved a constant omega. And we went about, we constructed the Noether current. G and G bar made our life very simple. So if you go to the previous page, you can have a summary of what we did. So G and G bar enabled us to write the interaction, write the Noether current, the U1 current like this in terms of G and G bar. And then what we did was we simply used the equation of motion for G and G bar. So we wrote down the full action, derived the equation of motion for G and G bar, and then we replaced G and G bar in the action by their equation of motion, by the solutions of their equation of motion. And this is the action we got. And I skipped a step here, which is left as an exercise. So I derived this action directly from here. This is just a very simple algebra. You can get this very easy. So once we have this, then we notice that, wow, this is something very strange. It's a strange kind of action. Because now we see what the interaction is. So if you write this up completely, yeah, we can do that. Perhaps that's probably worth doing. So if you write it up, well, we go to the next page. So let me go to the next page and write out this full action. So what is this SF? The SF is integral d4x, and then dA phi and bar of dA phi, we expand it out, and what we get is del A phi bar. Okay, then I think it's a plus sign, or maybe it's a minus sign. Well, one thing we know is that there will be a term which is plus mod phi squared AA. Okay, and then we have a term which is simply the Noether current. So I'll simply write it down as JAAA. You know the Noether current, so that's what this is. And so in addition, we have minus P of mod phi squared, and we have minus 1 over 16 pi C FAB. So that's our SF. So what we notice is that, okay, so JA has this structure of I phi, I think it's a plus sign, but I'm not 100%. Phi del A phi bar minus phi bar del A phi. Just check. So I'll just put a little wiggle, check this. Okay, so now what we see here is that there are two couplings. One is this kind of coupling, this JA kind of coupling. Okay, so that's linear in A, but we also notice this kind of a term, mod phi squared AA. And this is origin of Higgs mechanism. I mean, that term is really the origin, because you see, we have a completely U1 local gauge invariant action right here. We have not violated any gauge invariance, and yet we have an AA term multiplied, of course, by mod phi squared. Why do I keep harping on this? Because remember that when we just put a mass squared term in the Maxwell action, we called it the Broca action. In that case, the Maxwell action became not gauge invariant. If we put an m squared c squared AA kind of term, the action became gauge non-invariant, right? because AA term is not gauge invariant. But here we have derived it as a part of a full action is now gauge invariant, because that's what we derived just now. So this action fully is gauge invariant, and therefore the Higgs mechanism is nothing but why did it get the Nobel Prize? So that's what I'm not going to explain the Higgs mechanism. So it is a gauge invariant way. That's the most important thing. Way to give mass to a field. To give the mass to the electromagnetic field, this is the way it happens. I'm not explaining that to you, but I'm just saying that this is the origin. Excuse me. See, the point of fact here is that here we have the abelian Higgs model is completely U1 local gauge invariant. Omega is a function of omega x, and if I make those transformations with omega as a function of x, the action is gauge invariant. Action remains invariant, it's symmetric. Well, it's invariant. Now, what I wanted to say is that this is something spectacular because we didn't put it in. So there you can say that there's been an enlargement of the invariance group. Earlier, the invariance group was simply U1 with a constant omega. But now we have a much larger U1 group, which is called local U1, where the parameter of the transmission is an arbitrary function of spacetime. So gauge invariance is now a derived object, is a derived lesson from our derivation. That is the virtue of this. It came out from the way we did the Noether couple. Okay? And it also then is responsible to give a mass to the A field. Now, you could say that, why do you want to give a mass to the A field? Electromagnetism is a long-range force and there is no need to give a mass. I agree. But remember that Higgs had proposed this as a toy model. And the toy model is going to be generalized to explain why the weak interaction is short range. So what will happen is that this A, we shall not talk about the A of electrodynamics anymore. That will always be massless. We don't want to give a mass to the A field because that's a long range field. But we do want to give a mass to something that looks like an A field in weak interactions. So then the path to having a weak interaction which is short range, using the dynamics that we have discovered right now, becomes open. Okay, so we have a straight path now. Yeah.
So how the mass of the field and the long term and short range interaction depends?
So I actually told you this in one of the classes where I said that if a field has mass, right, then the range goes inversely as 1 over mass.
You told that just by we never derived it.
No, we didn't derive it. We can derive it, but we won't derive it now. So the point is that we know this. So the point is that although the Higgs mechanism can be used to give the photon a mass, we won't want to use it for giving a mass to the photon because the photon does not have a mass in reality. So, so the point is not that we know how to give the photon a mass. The point is that if there is something like a photon, which is not a photon, something which also mediates any other interaction, like the weak interaction, then the Higgs mechanism, you see, the emphasis here is on the mechanism. We have discovered a mechanism. Now, we have discovered this mechanism in the context of photons, but it is generalizable to a much larger context when you have the context of weak interactions. So even if the photon does not give a mass, and of course, there are details in the Higgs mechanism which I'm not telling you right now, it is possible to use the same mechanism to give a mass to the weak vector boson, to the vector boson, to the vector field, which mediates the weak interaction. In the same way, it's very much the same way. So I just wanted to give you a glimpse of what Higgs did why he deserved the Nobel Prize. He deserved a Nobel Prize because he found this mechanism. Now, if the photon was short range, if the electrodynamics was a short range force, then this would have worked for electrodynamics as well. But we don't want to use it for electrodynamics. And there is a way to arrange things in such a way that the electrodynamics remains a long range force, but the weak interaction becomes a short range force. And that is the essence of the electroweak theory. The electroweak theory tells you that you use the same mechanism to leave the photon massless so that electrodynamics remains long range, but you give the photon, the mediator of weak interactions, a mass so that that becomes short range. Okay, so there is this thing that the Higgs mechanism can do beautifully. Okay, and I would say that it deserves the Nobel Prize. Okay, because its mechanism was not there. If we try to give, so of course, you see, with photons, we will never try to put in an AA term in the action, in the Maxwell action, because we know that that violates gauge invariance. But if somebody tells you that we have something like a vector boson, a vector field, which mediates the weak interactions, then you might be tempted to do that kind of a thing for that weak interaction field. But then you go wrong because the weak interaction field also needs to be gauge invariant. You can't break gauge invariance. You run into big problems if you do. The particular problem of breaking gauge invariance is that then you're saying that your choice will influence nature. Because if you break gauge invariance, then you're breaking it your way, and whatever way you break gauge invariance, you'll have a difficulty in making sure that your predictions do not depend on your choice. So what we do in the Higgs mechanism is we now know that there exists this gauge invariant way to give mass to a vector boson, vector field. This mechanism is the great discovery of Peter Higgs. All right, so that's what I wanted to show you. But as far as our question is concerned, you see, as far as our question is concerned, it is answered. So yes, the U1 symmetry that we started with indeed can be identified with U1 electrodynamics if we go through the Noether coupling, because then we did see this aspect of U1 gauge invariance, which came out. We did not put it in by hand. We were always working, keeping the global invariance in hand. Then we did the Noether coupling. Then we replaced the G and G bar by using their equations of motion. And what came out was a theory which had this local gauge invariance. So local gauge invariance was a result we derived from our Noether coupling. This is what I want to say today. All right? Okay, so I hope all of you stay safe. All right, and if you have questions, I can answer, or else we can call it a day. It's almost over, 11:30.
Can you suggest any reading?
Yeah, I said there is no textbook. So the first thing you have to do is to go through every mathematical step of this lecture, right? And I'll of course